made it 15 instead of 5 like it was. So we did number 1 yesterday. I need to take it off of one of the sets of notes. All right. So these problems are still, you know, a little bit like, why do I want to know this? But there can be greater context where it could be more important. For the example I could maybe think of, I think it just makes it much more difficult to deal with, but like this one's talking about a pebble being dropped into a calm pond, causing ripples in the form of concentric circles as shown. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? So, obviously, if you drop a pebble into a pond, you're probably not so concerned with the rates that those are changing. The thing I could maybe think of that would be similar but much more important would be something like if you had like tidal waves or something. If you have like you've got a center of that where you have, you know, or the earthquake in the ocean or whatever has caused it, and then it goes out from there. I think probably the reason we don't see examples like that is because the curvature of the earth makes it where you really need to use like spherical geometry instead of flat plane geometry, and it technically would be much more complicated if you do that. But you can kind of, some of these like principles could be extended to, you know, a situation where you're going to care about it a little bit more. So it tells us the radius of the outer ripple is increasing at a constant rate of 1 foot per second. So we know the radius is 1 foot per second, but we're looking at the rate that the area is changing, right? So we care about the area. Is the rate of the area going to change at 1 foot per second? It is not. Why is it not? What? It's a circle. And how do we find the area of a circle? Pi r squared. The radius is squared, right? So you're not going to have the rate increasing at the same, you know, linear fashion that you have just for that length increasing. You know, if we were looking at something different, like if we were looking at the diameter, right, because the diameter would still increase linearly, it'd be 2 feet per second instead of 1 because it would be twice the radius. But the diameter would still, we could figure that out without having to use any calculus. But because we're looking at area where that radius is squared, it's going to be different. So whenever we're doing a problem like this, we need to think about what it is asking us. And it says when the radius is 4, at what rate is the total area of the disturbed water changing? So we're looking at there the rate of the area. So if I'm looking at the formula A equals pi r squared, what is this question asking me to find? What variable? Not A. A prime or dA dt. We really want to use dA dt here instead of A prime. The reason we want to use dA dt is because A prime would sort of indicate that it's with respect to the variable in the problem, whereas when we have dA dt, we know what variable we're dealing with respect to. So this is asking us for dA dt. That's what we're trying to find. So if we're trying to find dA dt, that means we need to take the derivative of the area formula, right? Now, the area formula only has one other variable in it. We have some information about our radius. So we don't need to try, some of the other problems we needed to try to get it all in terms of one variable because we had like length and width, but we only have one variable here. So we can just take the derivative of this, derivative of A would be dA dt. And we've got pi r squared. What's the derivative of that? 2 pi r dr dt. Okay, so the dAdt, that's what we're trying to find. We don't want to replace it. Do we know our r? R is 4. And we know dr dt. It is 1. So the radius is increasing at a constant rate. So dr dt equals 1. So we know what that is. So we have everything we need to replace here. So this is a pretty straightforward problem as far as these problems go. So dA dt is 2 pi times 4 times dr dt, which is 1. So that would be 8 pi. And what are our units? Feet squared per second. How did you know to use feet squared? Huh? Right. Right. I could not figure out why the units didn't work the other day. Typically the units work. But I couldn't figure out why the way that we did it that the units didn't work. I just couldn't ever figure out. But what Connor is saying, and this is helpful here sometimes, when you're doing dA dt, if you include the units in the problem, so you got 2 pi times 4 feet times 1 foot per second. For this, this is over 1, this is over 1. If you include the units, 2 pi times 4 times 1 gives you 8 pi. And if you look at your units, feet times feet gives you feet squared. And then 1 times seconds, you get over seconds here. So your unit, you could include the units as you do the problem, and it will automatically give you the correct units. It also helps you know that you did it right if you get units that make sense here. So you can leave units off and just think about it at the end, or you could include units as you do the problem. Okay, yes? You need to think, so we're looking for dA dt, so we need to think about how we measure area. And so since this one uses feet for the radius, when we're talking about area, we're going to have feet squared, because for area, we would use square feet. So your area is going to be feet squared, and you're looking at this with respect to time. So you're going to look at whatever time was used for your rate up here, so feet per second, so that we're using seconds. So that tells you you have seconds here. Because it's a rate, it's not just going to be square feet, it's going to be square feet per second. Okay, questions? Now, this is not going to be the same at every point. Because if we are looking at the point where the radius is 8 feet, then it'd be 2 pi times 8 times 1. And so we'd have 16 pi. So that area is increasing at an increasing rate, right? Because adding 1 inch or 1 foot to the radius is going to add a larger and larger and larger area to what has been disturbed here. I wonder to what extent earthquakes this would apply. This is like your damage area. Here, of course, the further away you get, the less damage you have. But yeah. I think that's one reason that we look at these problems that are, yeah, that probably could be. Yeah. So, anyway, I think the reason that we look at a lot of stuff like this, dropping pebbles into ponds, instead of earthquakes and well, nuclear bombs they probably leave off for, not encouraging nuclear war. Although, it's a good scientific thing to look at. But anyway, but I think the reason that we look at pebbles and ponds instead of much bigger things is because things like the terrain, things like, there's a lot more factors that have to be considered, and your answer is not going to be as accurate, whereas here we can have a fairly accurate answer. So. Okay, so here's a new one. Okay, so I always think that I need to get some spherical balloons for this, but I don't even think I have any regular balloons. Air is being pumped into a spherical balloon. So imagine that you have a balloon that is perfectly round. Yeah, that actually would be a very good example. Yeah, that actually would be a very good example, but if I let the air out of it and try to blow it back up, it takes a while with the little hand pump thing, so I'm not going to do that. But that would be a very good example, because at first it's going to be collapsed, right? But once you get it to the point where it's the spherical shape, right, with each, pump that you are putting in there, the ball is going to get a little bit bigger. But there towards the end, it just seems like it's taken forever, right? Because it's just expanding just a little bit. So whenever you blow up a balloon or a ball or whatever you're blowing up, usually you are blowing it up and your volume is changing at a constant rate. Particularly if you are using like a pump to blow it up and not just like blowing it up with your mouth. But even with your mouth, if you have generally standardized breaths and are, doing each breath the same, each breath is going to have roughly the same amount of volume. Less standard. But if you're using a pump, you can know how much air is going into that balloon. So air is being pumped into a spherical balloon at a rate of 4.5 cubic inches per minute. Find the rate of change of the radius when the radius is 2 inches. So this time our volume is changing at a constant rate. Is our radius going to change at a constant rate? If you picture what's happening there. Because at first, the radius is going to change a lot, right? Whenever you blow into a balloon, it goes from flat to little balloon to bigger, bigger, bigger. But then, like, whenever you get it almost blown up, each breath, it just gets just a tiny bit bigger, right? And a tiny bit bigger and a tiny bit bigger until it either pops or you tie it off, right? So that radius, we should see it changing at like a decreasing rate. It's going to increase faster at first and then slower. What's the question asking for? What variable are we trying to find? dRdt. Rate of change of the radius. That is dr dt. That is what we're looking for. Okay, what do we have? Okay, we have r equals 2. Now, does r always equal 2? I should have asked this on the last question. Is the radius always 2? No, the radius is changing. So this can only be plugged in after you take the derivative. Now, if we were dealing with something where the radius was always 2, which wouldn't be the case because then your rate of change of the radius would just be 0 for this, but we could plug it in before we take the derivative. But we can't plug this in until after we take the derivative, but r is going to equal 2. What else do we have? What is this 4 cubic inches per minute? or 4.5. That is your rate of the volume change. And what variable would it be? dV. dt is 4.5 cubic inches per second, or per minute. All right, R is 2 inches. dr dt is what we're looking for. All right, let your units help you with deciding what you're dealing with here. Cubic inches, anything cubed is going to be dealing with volume, right? If you have a distance squared, you're dealing with area like we were on the last problem, so that can help you. So we need the volume formula for a sphere. Everybody know it? It is 4/3 pi r cubed. I think on most questions that are going to be on the AP exam, they are going to give you that equation. They don't. You never have a formula sheet, but they may embed they'll give you the volume of the sphere is 4/3 pi r cubed in the problem. So I think that will probably be given to you. I'm not going to spend time making you guys memorize that. There's a chance. There's no guarantee. They don't have an inclusive list of all the formulas that they're going to give you, so there's a chance they may not, but I think they usually do. So if we have this volume formula and we're looking for dr dt, we have dv dt, we need to take the derivative of this. So let's see, Cade, what are we going to get when we take the derivative here?
4/3 times pi times 3r squared.
We need one more thing. Good. dr dt. And that will give us dv dt. That 4/3 pi is just a coefficient, so it can stay out front. And if we simplify this a little bit, that 3 right there can cancel with this 3 in the bottom, so we get 4 pi r squared dr dt, which, interestingly, is the surface area for a sphere. And now that we've taken the derivative, we're going to plug in the information that we know. So we know dv dt is this 4.5. We know that this radius right here is 2. And we don't know dr dt, but that's what we're trying to find. So we'll have 4.5 equals 4 pi times 2 squared dr dt. And since this problem has decimals, I'm going to assume they probably just want us to give a decimal answer. Did I show you guys what Coach Popham got me? Isn't it cute? He was my secret Santa. Alright, so 4 pi times 4 pi. So we got 4.5. We're 4 times pi times 4 is, we got 4.5 equals 50.2655 dr dt, and then we'll divide by that 50.2655. And we are going to get 0.089525. What are our units on that? What? Inches per minute. Because it is, you're looking for dr dt, right? So how do we measure radius right here? The radius we would just measure in inches, right? And then time is being measured in minutes here. You can. So if I go back to show you how to do this with the units. Some students don't like to do this, but if you go engineering, science-y sort of route in college, I know my husband said this is something he did a lot in engineering school, dealt with just like units almost solving the problem for you. So when you put in 4.5, that is inches cubed per minute. And it equals 4 pi times the radius, which was 2 inches squared, times the dr dt, which was, what was it, 1? No, we were looking for dr dt. All right. So this 4, what happens here when you square this, you got 4.5 inches cubed per minute equals 4 pi times 4. When you're squaring the 2, you also square the inches. So 4 square inches dr dt, which is giving you 4.5 inches cubed per minute equals 16 pi, or that 50.2 whatever inches squared dr dt. So when you divide here, you're dividing by 16 pi inches squared. So we just did 4.5 divided by the 50.265, which is your 16 pi. And that gave us our answer. But you can also deal with the units there. So you're doing inches cubed over minutes divided by inches squared over 1. So that would be inches cubed over minutes times 1 over inches squared. And so these 2 inches here are going to cancel with 2 of the inches here, just giving you a single inches in the top and minutes in the bottom, which is your units for that. It sounds like you guys have looked at, yeah, you've probably done that a lot. But have any of you guys done problems with, the rest of you, have any of you guys done units, like problems with the units in the problem like that before? You have, what class did you do it in? Aerospace, yeah. I should probably do it more. It really is. There's enough of you considering engineering science sort of routes that it is very helpful. I'm going to do it on the next problem also. You can just wait till the end. You can ignore units. You can do dr dt. R is measured in inches. T is measured in minutes. So your units are inches per minute. You can ignore it and think about it at the end. I find it particularly helpful whenever you're using units that you're not as familiar with. You know, like newtons and ohms and whatever else. Yeah, joules, whatever. All those things, I can't even really tell you where they go. When you're using unfamiliar units, I find it a lot more helpful to use them in the problem, because here I know that I measure my radius in inches. If you're asking me for the resistance of some electrical current, like, it's my own fault, but I don't know what units I use for that, so it makes it more difficult to know. No, I guess if you were really good. All right, I love this problem. I love this problem. The only thing I don't love about this problem is I do use S as variable, which is a little bit annoying. But I love this problem. It came from the textbook, because now this to me seems like, oh, I think somebody uses this somewhere. Once again, if you're actually using calculus in your daily life and you're not a math teacher, you are probably doing something. Because the person flying the plane doesn't know this. The person operating the radar in this building probably doesn't know this. But whoever designed the radar, whoever programs stuff, somebody's got to be thinking about stuff like this. So an airplane is flying on a flight path that will take it directly over a radar tracking station, as shown. If S is decreasing at a rate of 400 miles per hour when S equals 10 miles, what is the speed of the plane? So to me this makes a lot of sense because this little radar, satellite or whatever thingy here is got to be measuring like the distance to the plane. But what it really wants to know is how fast the plane is going, right? But it's measuring the speed at which S is changing, right? Because it is, bouncing off. What's radar? Yeah, its waves bounce off and come back. So it's dealing with the distance to the plane from where it's at, not the plane's actual speed, right, as it is relative to the ground. But it wants to know the speed relative to the ground. So in this particular case, this plane is maintaining an altitude of 6 miles, which makes the problem easier. If the altitude is changing, also makes it more difficult to do the problem. But it still can be done. It just makes it a more complicated problem with more variables. So they want us, let's try to piece together what S is decreasing at a rate of 600 miles per hour. So S is decreasing at a rate of, I'm sorry, not 400. It's 400 miles per hour. What does that tell us? What variable is that? ds dt equals what? Negative 400 miles per hour. I'm going to do units in this problem. So I'm going to write it mi over hr, so miles over hours here, because it makes it easier to deal with your units. S is 10, but is S constant? It's not. It's changing, right, because that plane's moving. It also doesn't say S is constant either, so both of these things could possibly be changing. And it wants to know the speed of the plane. So speed of the plane is what it wants to know. What is that? If we're looking at this diagram, what? It's not X. X is the distance there. It's the derivative of X. Because X is this distance, and if we can find the rate at which that distance is changing, that is the speed of the plane, right? Because the plane is going on that path. The plane is not trying to, kamikaze into the building right here. It is going this way. We are speed of the plane, that is dx dt. That's what we're looking for. So we need a formula to start with that relates x, 6, and s. What formula could we use? Yep, Pythagorean theorem, right? So we know x squared plus 6 squared equals s squared, right? So we could go ahead and take the derivative of that, and if we do that, we will get 2x dx dt, 6 squared, that's just going to be 0, and then we'll get 2s ds dt. And so that dx dt is what we're trying to find. We don't want to replace it. I know ds dt. I know S. I don't know X, but we can find it, right? So I'm looking for that X right there. I can plug back into the original problem, the Pythagorean theorem, right? So if I think about what that looks like, I know that S is 10. I know this side right here is 6. I'm looking for X right there. X squared plus 6 squared equals 10 squared. So X squared plus 36 equals 100. X squared is 64. So X is plus or minus 8, but for this particular case, 8 is all we need. Yep, it's 3, 4, 5 triangle with a dilation factor too. It's not. Usually textbooks draw the picture to scale, even though they warn you it's not drawn to scale. It is not drawn to scale here.
I mean, well, the jet takes up about a mile.
Yeah. Well, and we also must consider that jet is moving, so it's not. It could be an accurate picture, but not at the moment that they're asking for, because X should be longer than. Yeah.
Look at it. We get compared to X. X is equal to 8 miles, right?
Yeah.
That jet.
Not to mention how gigantic the building would be.
The building, yeah, the boat's probably too.
Yeah, compared to the 6 mile. Yeah. So, a lot of times when they tell you it's not drawn to scale, they don't really mean it. They've drawn it to scale, but
That building's about as tall as the mountain.
it's not drawn to scale here. So, let's plug everything in. So, we've got 2 times 8. We're not going to plug anything in for dx dt, because that's what we're trying to find. Oh, wait. I told you guys we were going to use units. I need to mean it. Let's use units. What is x measured in? X is in miles, because it's just a distance, right? What is S measured in? Is also miles. Okay, so I'm going to include units on this. You don't have to. You could do this without units and just think about what they should be at the end. But I've got 8 miles dx dt. I don't know, and I need to find. 2, S is 10 miles. ds dt is negative 400 miles per hour. So over here, we've got 16 miles times dx dt. On the right-hand side, you can think about putting everything over 1 here. So you've got 2 times 10 times negative 400, which is going to give you negative 8,000. And then when you're thinking about units, in the top, you've got a miles here and a miles here that are being multiplied together. So that gives you miles squared. And then in the bottom, you've just got hours. Okay? Are we okay here? We are solving for dx dt, which means that we need to divide both sides by that 16 miles. So dx dt is going to equal, you got your 8,000 divided by 16, 500. So we got negative 500. And then watch what happens with your units. This is miles. You can put it over 1. So if you are thinking about that, that means miles squared per hour And then dividing fractions is easy as pie. Flip the second and multiply. And so one of these miles cancels with one of these miles here. And you just get miles per hour. So miles per hour. Now technically this is not the answer. That is the velocity. Because it has a sign, right? What did the question ask us for? Speed. Does speed have direction? It does not. So it's just 500 miles per hour would be your answer. If they asked for velocity, though, you would need that negative. So I have to think that somewhere inside of radar stuff, there's computers doing stuff like this really, really, really fast, and that the people actually using it don't think about it. But somebody had to think about it for it to happen, which is pretty cool to like know how it works, even if it's, you know, I think it's pretty cool. Now, I worked that whole problem with units. I think it's cool to work with units. You are not required to work with units. So if you left off units and at the end you just said, well, X is measured in miles, T is our time, which is hours here, so the units here are miles per hour. You must include the units at the end, but I'm not going to require you to work with the units through the problem. But no, as far as I know, I have never seen any requirement for that. You must put units on your answer at the end, but you don't have to work it out with units. However, I do feel like if you are going into some engineering or science, there's a strong chance you might encounter some professors that do require you to use units. It seems like in college I had some that required it, and maybe some physics. Yeah. So it's good, just good practice if you're headed that way. If you're not, you might be like, good enough. All right. So you have these problems here. Let me look through them. Let's see if there's any. I don't remember this card. Let me tell you that number 22 has a picture, but it's easy to miss it because it's not right there with 22. It's below 21. Okay, so it's like the problem goes on to the next column, but there is a picture which will help you a lot on that. 25, that is a picture looking down on the planes like you're viewing them from space. That picture confuses students a lot, but it's like you are above the planes looking down as they fly. And let's see if I need to tell you anything about 26. And 26 is basically the problem we just did, but with a few little things changed about it. Yes, please. it'll just be basically like once you get everything set up, it's just going back and plugging different numbers in, so it shouldn't take you very long. Radius or volume of a sphere is 4/3 pi r cubed.